All right, so now we're going to talk about relative homology. Okay, and the basic idea behind this is that we're going to look at, instead of a single space, we're going to look at a pair of spaces. And we're going to more or less say that if a chain is supported in the smaller space, then we pretend that it doesn't exist. Okay, and more or less that has to do with looking at quotients of the chain group. Okay, so so let's set it up. So let K be a simplicial complex, and then K0 be a subcomplex. Okay, of K. All right, then this leads to the idea of the relative chain group. So the relative chain group, which I denote by CP K comma K0, right, is just the quotient of the chain groups of K and K0. So this basically means that CP K comma K0, right, is defined to be CPK quotiented by CP K0. Okay, so obviously we've seen quotients before. It's like in defining homology, and so in essence what happens is that instead of looking at the elements of this quotient space are the cosets, it's like of CPK0, right? So the general element of CP K comma K0, right, has the form C plus CP K0, where C is an element of CPK, right? So it is a coset. Okay. Okay. So so this is so the quotient partitions CPK into cosets, right? Which consist of basically p chains in K, right, which are the same on K excluding K0, but may differ on K0. Okay, so this is basically what those cosets consist of. Okay, all right, so once you defined this idea of a relative chain group, the next natural question to ask is, can you talk about a relative homology? Okay, and the way you do this obviously is that we need to think about how you can construct a sort of relative boundary operator, if you will. Okay, so let's see what happens. Okay, so you know that in the usual spaces you have these boundary operators at the level of the chains, okay, and then you want to look at something similar, but now at the level of the relative chain groups. Okay, so I want to look at an induced boundary operator. Okay, so so we know that if you have a map C, this maps to C plus CPK0, right? And then obviously C maps to the boundary of C here, right? And then the boundary as C maps to boundary as C plus Cp minus 1 K0. Okay? All right. So the basic idea, if you will, is that the way the boundary operator is like at the unquotiented space induces a boundary operator in this quotiented space, which is the space of relative chains, is that given an element C plus CPK0, right, in CPK comma K0, right, what you do basically is you map the representative element, which is C, right? You map C to boundary of this, and then you consider the coset, and this is of course in Cp minus 1k, associated with Cp, well, boundary PC, okay, which is this boundary PC plus Cp minus 1 K0. Okay, so that's basically how you construct this induced boundary operator, right? Is that you take a representative element, it's like in this coset, right? You map it, it's like by the usual boundary operator, and then you look at the coset associated with the boundary of that representative element. Okay, then you have to show obviously that this coset is well defined, irrespective of what choice you've made. It's like of the representative element here. Okay, and that sort of shows you that that induced map is actually a well-defined map on this quotient space. Okay, but that's sort of easy to check. Okay, so so some remarks are that so you can also check that the boundary is the identity. I'm sorry. So you apply the boundary twice. It's like then you get, well, I guess technically it would be something like boundary p minus 1 boundary p is equal to the sort of 0, right? Okay, so all right, so now that you have an induced boundary map, it's like at the level of the relative chain groups, then you can construct all the sort of the relative cycle groups, the relative boundary groups, and the relative homology groups, right? So let me just sort of say that. So now, right, we can have sort of the relative cycles, relative boundaries, relative homology. Okay, all right, so so the relative cycles, right, Zp ck comma k0, right, is the kernel of this boundary operator, but the induced boundary operator on the relative chain group, right? And then we have the relative boundaries, right? So that's sorry, Bp k comma k0, right? And this is the image of the boundary operator for dimension p plus 1, and then sort of the relative homology, okay, which is hp k comma k0, which is the kernel of the p boundary operator, quotiented by the image of the p plus first boundary operator. Okay. Yeah, so you know, it's like, so that's sort of the obvious thing. And then so to distinguish sort of the homology K, right, from the pair K comma K0, right, we refer to HPK, right, as the absolute homology. Of K, and the elements are the absolute classes. Okay, and then so one other thing is that the same way that continuous maps induce maps at the level of homology, right? Continuous maps between pairs of spaces also induce, you know, sort of maps. It's like on relative homology. Okay. So continuous maps induce continuous maps between spaces. Induce maps on homology. Right, and then if you and this extends to relative homology as well. Right, so if you have a map F from K to L, where K and L are simplicial complexes and subcomplexes, let's say K0 is contained in K and L0 is contained in L, and then F maps K0 into L0, then we have an induced map. Let's call it F sharp, okay, between the chain group of K, K0 to the chain group of L, L0. Okay, and then which commutes with the identity, with the boundary map. Okay, and then as a consequence of that, that induces a map at the level of relative homology. Right. So F star is a map from HP K comma K0 to HP L comma L0. And a particularly interesting case, right? One important case is sort of the map, the induced map which comes from the map K comma the empty set to K comma K0. And of course, it's like the reason is because when you have a pair K comma the empty set, this really is sort of associated with the absolute homology, right, and the absolute chains, if you will, right. So if you're quotienting by the empty set, then you essentially just have the original space itself. Okay, so so that's basically what I wanted to say. It's like, and then the next thing we'll talk about is this idea of excision, which we'll see in a little bit.